Hi students, in this section I'm going to talk to you about correlation. I'm going to show you some hand calculations and also some corresponding SPSS output. My name is Dr. Marie Wong. So what I have to begin with, I have some data to get us started. What I have is I have a data set based on 5 individuals. And remember, with correlation, we have an X variable and we have a Y variable. So for each individual, we're going to have a score on X and a score on Y. So for example, individual A, their score on X is 0, the score on Y is 4. Individual B, the scores are 2 and 1. Individual C, the scores are 8 and 10, and so on. So you can see some things should look familiar here. You can see that for X, if I sum up those X scores, if I take 0 plus 2 plus 8 plus 6 plus 4, I'll get sigma X of 20. Remember, sigma X simply means we're going to sum the X scores. So I just add up those scores, I get a sigma X of 20. For the Y column, if I take those numbers and I sum them, I add them up, sigma Y is going to be 30. And then this is something new in correlation. We're also going to calculate what's called a cross product. What that means is we're just going to take for each person, we'll take that person's X score times their Y score. And that's what that XY is. And then we're going to sum those XYs up. So for example, for XY, for person A, if I take 0 times 4, that gives me 0. So 0 is my XY for person A. For person B, I take the X of 2 times the Y of 1. 2 times 1 is 2. That's my XY for person B. For person C, 8 times 10 is 80, and so on. So I can also do a sigma X of that column. So it just means I'm going to take all of those XY products and sum them up. So 0 plus 2 plus 80 plus 54 plus 24 will give me 160. That's my sigma XY. Then finally, the last thing in here, and this should probably be familiar to you also, is we can take all of our X scores and we're going to sum them. That's to calculate sum of squares later. So if I take each of my X scores and square them, and then I sum them, so to square 0, I get 0. To square 2, I get 4. If I square 8, I get 64. Squaring 6 will give me 36, and squaring 4 will give me 16. So that X squared column, I'm just taking all of my X values listed in the X column and squaring them, and that's giving me the X squared column. If I sum up X squared, it gives me 120. I just get that from adding the 0 plus the 4 plus the 64 plus the 36 plus the 16. Then finally, the last column, Y squared, it's the same exact thing, except for instead of using X's, I'm using Y's. I just take each of those Y's in the Y column, I square them, and then I sum those squared Y scores. And that's what sigma Y squared is. It's just the sum of those squared Y scores. So 16 plus 1 plus 100 plus 81 plus 36 gives me 234. So now we have what we're going to need to calculate the correlation by hand. Again, sigma X, we're just summing up the X column. Sigma Y, we're summing up the Y column. Sigma XY, we're summing up the column of X times Y. Sigma X squared, we're taking all of our X's and squaring them, and then we're summing those. And sigma Y squared, we're taking all of our Y's, we're squaring them, and we're summing those. Okay, so that's all there on that table for you. We're going to come back to that bottom line of numbers, all those sigma X's and sigma Y's and so on. We're going to need those to calculate our correlation by hand in a few minutes. But before we do that, I want to remind you of a couple things. Before we do our hand calculations, I need to talk to you about the hypotheses and also about the critical value. So when we talk about the population, when we're talking about correlation, we use the symbol rho. So what we're saying here is basically the population rho is going to be 0. In other words, the correlation between X and Y in the population is going to be 0. I also am using my research hypotheses, H1. I'm simply saying here that the correlation between X and Y is not going to equal 0. It will be something else. It's something that is not 0. That's a two-tailed hypothesis. And remember, a two-tailed hypothesis, that's when we simply say that there's going to be an effect, but we don't specify a direction. If I were going to make this a one-tailed hypothesis, I would be specifying either that rho was going to be greater than 0 or less than 0. In our case here, I'm not specifying. I'm simply saying I'm making it a two-tailed test. It's a two-tailed hypothesis. I'm simply saying that that whatever we get, it's not going to equal 0. It's going to be different than 0. So again, as I've mentioned, that's a two-tailed test. If we set alpha at 0.05 and our degrees of freedom, the formula for degrees of freedom for correlation for Pearson's R is n minus 2. So I have 5. My sample size is 5. That's the number of participants I have. So 5 minus 2 is 3. So my degrees of freedom here are 3. So what we do, like we've done with all the other tests, to get our critical value, we would find a table. We'd find an R table. And that table would, we would indicate on the table if we were doing a one-tailed versus a two-tailed test. We would set our alpha at 0.05, and we would choose the value that corresponds to degrees of freedom of 3. So if you went to one of those tables, either in the back of a textbook or you could look it up online, you'll find the critical value that corresponds to those values is plus and minus 0.878. So that's going to be our critical value. If I get a correlation that's bigger than 0.878, so if I get a positive correlation higher than 0.878, or if I get a negative correlation less than 0.878, I'm going to reject my null hypotheses. Okay, so now what I want to do is we're going to do some hand calculations here. So I want to show you by hand, I'll show you some basic formula to do a correlation by hand. What I want to show you first, we have to calculate 3 different parts before we can calculate our correlation coefficient R. This is my step A, and this is going to be my sum of products. So the formula for that is sigma xy minus sigma x times sigma y divided by n. So that's going to give me my sum of products. And we've already calculated these. If you remember the column, I went through all of these numbers. So in this case, sigma xy, if you need to go back to that column, that table, you'll see sigma xy is 160. You'll also see that sigma x is 20 and sigma y is 30. And my sample size is 5. Okay, so what this is then going to give me when I do my math, it's simply going to be 160 minus 120 is going to be 40. Okay, so 40 is my sum of products. This is going to end up being the top part of my correlation coefficient, my formula for the correlation, the sum of products. This is basically the variance that's the covariance between x and y. All right, my next step, we're going to calculate summa squared x. So hopefully this is familiar. We've done this if you've been following along on these different videos. I've shown you multiple times how to do summa squared, but let me just refresh your memory. So the formula for summa squared x is sigma x squared minus, in parentheses, sigma x squared divided by n. Okay, so what we're going to do, sigma x squared is 120. We already calculated that, minus sigma x in parentheses. So remember, sigma x in parentheses is not the same thing as sigma x squared. Those are different things. Sigma x squared is when we take all of our x values, we square them, and we sum those squared values. Sigma x in parentheses squared is when we sum all of our scores, all of our x's, then we square that sum. All right, so my sigma x is 20. So I got to put that in parentheses. I'm going to square that. And I need to put my divided by 5 there. So I'm just going to do my math. This is going to give me 120 minus 80. And my answer here is going to be 40. Okay. We just happened to get 40 twice in a row. I had to look there twice and make sure. I was like, that is correct. All right. Something else I need to do before I can plug this all into the formula for correlation. You can probably guess. I not only have to calculate my summa squared for x, but since we have y's also, we have to calculate my summa squares for y. The formula is going to look the same as this for the summa squares of x, except we're going to plug in y's. We're going to put y's in there instead of x's. So the formula here is just going to be sigma y squared minus sigma y in parentheses squared divided by n. Okay, so sigma y squared, that is 234. Minus 30 in parentheses squared divided by 5. So when I do my math here, I'm going to get 234 minus 180 is going to be 54. Okay, so that's my sum of squared y. So now I have all the parts that I'm going to need for my formula for correlation. And let me show you the formula for correlation down here. For Pearson's R, the formula is going to be sum of products divided by the square root of sum of square x times sum of square y. Okay, and we've just calculated all of those things, right? So our sum of products is 40. Plug that right in there. My sum of squared x is also 40. And my sum of square y is 54. But don't lose your square root sign. It's tempting to forget the square root sign. Don't do that. So now what I'm going to have here when I do my math is I'm going to have 40 divided by the square root of 2,160. And then I have to take my square root. So 40, if I take the square root of 2,160, that's going to give me 46.148. Okay, so now to get R, I'm just going to take 40 divided by 46.148, and that's 0.86. So my R here, my Pearson's R that I just calculated, is 0.86. Okay. All right, so remember our critical values. Let me draw a little picture here. All right, so this is this would be where R equals 0. And remember my critical values. It was plus 0.878 for the positive end and minus 0.878 for the negative end. All right, so basically here's my cutoffs. Anything in these tails, we would reject our null hypotheses. So if I get a correlation coefficient that's greater than 0.878 or less than negative 0.878, I'm going to reject my null hypotheses. Okay, but look what happened here. Our R is 0.86. It doesn't quite make it. Here's where 0.86 is. So I cannot reject my null hypotheses. My statistic did not reach statistical significance. It is in this body part of my distribution. It is not in these tails, so I cannot reject my null hypotheses. So what I have to conclude is that my results are due to sampling error, that my results are due to chance, that there's not a statistically significant correlation between X and Y. So you might be thinking, well, wow, that was really, really close. The answer here would be my sample size is very small. And so what would happen is if I increase my sample size, what would basically happen is that my critical values would be less strict. My critical values would not be as high as they are. So getting a correlation of 0.878, that's a pretty strong correlation. So if I had a bigger sample size and I looked, that would affect my degrees of freedom, right? And then when I go to the table, I would end up having less strict boundaries there. And I would be more likely to be able to reject the null hypotheses. Think of it a little bit like if any of you ever ran track in high school and you had to do hurdles. I personally did, and I found hurdles to be horrifying. So I never really wanted to jump over them, and I liked when they were really low. So think about it this way. If these are like hurdles, these critical values, and you're trying to get your statistic over the hurdle in order to reject the null hypotheses. One thing you can do by increasing your sample size is sometimes the hurdle can be lowered a little bit. So then that makes it more likely that you could reject the null hypotheses. All right, so that gives you the hand calculations for Pearson's R, for Pearson's correlation coefficient. So what I've just done is I've shown you how to do hand calculations using raw scores to calculate Pearson's R. Raw scores are the scores that we begin with, the scores that we collect from our research participants. But we sometimes can have our scores in z-score units. And I just want to show you that we can get the same results using what's called the z-score formula. So the raw scores that we had in column X and column Y should look familiar to you, right? You've seen those numbers before. Those are our raw scores. The numbers in column X and column Y, those are our raw scores. I've calculated the mean and the standard deviation for those numbers. so that we can, for those columns, so that we could calculate the z-scores for each x value and each y value. Now, you don't have to do this on your own. I'm just showing you that this formula down below where r equals sigma zx times zy divided by n minus 1, that's an alternative formula for Pearson's R if you would happen to have z-scores instead of raw scores. And all I'm showing you with the zx and the zy column and the x and the y column is that I originally started with raw scores. I converted them to z-scores. That's what those formulas, the zx equals x minus the mean of x divided by the standard deviation of x. That's the formula for taking an x and converting it to a raw score. The same thing for z of y. If I take y minus the mean of y divided by the standard deviation of y, that y column there, that would be if I took each y score, plugged it into that formula, that would give me a z-score for that y score. All right, so the main thing to look at, so you could just assume that you were given z-scores. So you have the z-score for x and the z-score for y for each person. And then if you had that, that would be a really good situation for you for doing hand calculations, because in that case, if you're given z-scores, all you need to do is take zx times zy, that last column there. So for example, for person A, that person's z-score is negative 1.26 for x, and their z-score for y is negative 0.54. I would just multiply those together. That's where the 0.68 came from. So for each person, I take their zx score, multiply it by their zy score, and I get those numbers in that last column, zx times zy. Then I simply sum those. If I take sigma zx zy, I get 3.43. I can plug that right into my formula for R, my z-score formula for R. If you remember, my n is 5. I have 5 participants here. 5 minus 1 is 4. So that's where I'm taking 3.43 and dividing by 4. And that gives me 0.86. So notice we got the same number, right? We got this exact same value using the z-score formula versus the raw score formula. What would determine which formula you would use would be what your data, the units that your data are in. If your data is in raw score formula, is in raw scores, you would use the raw score formula. If your data has been converted to z-scores, you could use this z-score formula. Okay, so I just wanted to show you that there was an alternative formula for z-scores in case you needed it. Now, one last thing I want to do is talk to you about the SPSS output for correlation. And you can see it's very simple. So here, we're just looking at the correlation between x and y. If I took those values and put them into SPSS, my output, I would first get information on the mean and the standard deviation, the descriptive statistics for x and y. And then if you look, you see a table that says correlations. And you can see that it says Pearson's correlation, and you see an x and a y. So notice where there's a 1. Notice how there are 1s there. The 1s are when the variable's correlated with itself. So x correlated with x would give you a 1. Y correlated with y would give you a 1. But what we're really interested in is the correlation between x and y. So you can see there from that table, it's 0.861. So this is giving me the correlation between x and y, which is 0.861, which is what we calculated by hand. And notice the significance level, it's 0.061. Remember what I've taught you? That you need that number to be less than 0.05. We do not reject our null hypotheses. Our significance level, we do not have a statistically significant result here, meaning that we can't be sure that our result is not due to chance, that it's not due to sampling error. And then I just want to show you over to the left how you would rate this. R equals 0.86. And then we indicate our sample size with correlation with Pearson's R. Instead of degrees of freedom, for some reason we report sample size instead. And then notice the P. If our R was significant, P would be less than 0.05, but we did not get a statistically significant result. So because of that, P is greater than 0.05. What that's telling people, if they were to read a report where I wrote this, that would tell them that my results were not significant because P is greater than 0.05. Okay, so this is showing you, again, SPSS output using the same data that we calculated by hand. We put it into SPSS and we got the same results. We got the same correlation. And again, it was not statistically significant. We also determined that when we did our hand calculations. So this lecture, the purpose of this lecture was to show you very quickly how to calculate Pearson's R, and also how to interpret Pearson's R in using SPSS if you had SPSS output. Thank you.